Hi guys, if you are listening to this tutorial video, or it means that you are interested in vector error or autoregressive and vector error correction model in theory or in practice, or both in theory and practice. So in this tutorial video, we will show you how to build a model based on data, multiple data, and in which situation we need to use a vector error correction model or vector autoregressive model. So first of all, we need to know that a multivariate time series are different kind. We have vector error correction model that will come a little bit sooner on it back. We have a vector error correction model. We have autoregressive distributed lag model, and we have error correction models. So that are principal four time of vector of multivariate time series. So in VAR situation, we have, for example, a situation of two variable that we need to express each one in function of lags of the others. So we have, for example, we have prices on the market, and secondly, we have the demand. So we maybe need to express the demand in function of price and vice versa. So you can use this matricial representation in order to express a couple of variables represented by price and demand in function of lag vector, lag vector of price and demand. So you have the error term as in linear regression, but the difference here is that we express many variables in function of order. In this case, we have expressed a variable in function of lag variable. So this is the reduced form. We also have a structural form of model that lead to autoregressive distributed lag model. XT and YT could be both integrated of could be stationary or both integrated of order 1. The residual are integrated are stationary. So we also have a situation in which both XT and YT are stationary. We have a conventional stationary bar. So we have also this situation in which both XT and YT are integrated of order 1. So when there exists a beta, coefficient beta, so that XT minus B, YT minus beta XT is stationary, we have a problem of spurious regression. So in the situation in which both variables are integrated of order 1 and there exists a beta, so that xt minus beta yt by minus beta xt are stationary, we need to express a error correction model. So in a situation in which we have only one cointegration relation, this relation when beta exists, so that yt minus beta xt is stationary, we can say that there exists a cointegration relation between xt and yt. And in the case which we have only one cointegration relation, we should estimate a Engle and Granger test. We should make a Engle and Granger test to do that, to know that. So in the case in which we have more than one cointegration relation, we have to estimate a vector error correction and Johansen test. So vector error correction, Engle and Granger test is in the situation in which we have only one cointegration relation, and when we have more than one cointegration relation, we should run a vector error correction model and Johansen test. So we can have a situation in which we have more than two variables. So we have variable x1, x2, still xk. We have k variable, and in this situation, we have a VAR which is not just a relationship between two variables as previous situation that we presented to you in this tutorial, but we have multi relationship between variable and last variable. So we have a structural form of VAR, which is a situation in which we have all our variables that are in which x1 and x2 are integrated of order 1. We have a structural form of VAR that is given in your screen. And in this case, we talk about autoregressive distributed lags in our models. So in other situation, we what is VAR P, VAR of order P, instead of VAR of order 1. If we have, we take a situation of VAR of order 2, we can estimate our variable in function of 2-degree lag. So we estimate our variable, our couple of variable in function of lag variable of 1 period and lag variable of 2 periods. So in this situation, we have a VAR 2. So if we make a transformation, we can estimate this relationship so that any VAR P could be transformed in VAR 1. So we don't need to estimate in every term a VAR P. So this relationship permits us to transform any VAR P in VAR 1 by this transformation using companion matrix. So what is cointegration? As I told you very earlier in this beginning of this tutorial, there are two integrated of order 1 series xt and yt. If there exists a beta so that yt minus beta xt is stationary, we say xt and yt are cointegrated, or there is one cointegrating relation between xt and yt, and the state of xt minus beta of yt minus beta xt is stationary, which stationary is called the long run equilibrium between xt and yt. What do we run a cointegration test? So the method of Engle and Granger is given as so: we fit yt in function of linear relationship of xt. So we fit with ordinary least square, and we test if whether or not residual of the relation of this linear correlation estimation is stationary of order or stationary of order of integrated of order 1. So we should make sure whether or not residual of a linear regression between yt and xt is have an error term that is stationary or co-integrated of order or integrated of order 1. How to test stationarity of error term or versus integration of order when we have decay Fourier test and augmented decay Fourier test. So decay Fourier test is based on the assumption that if there is no drift or there is no drift or a linear trend, we have a linear relationship of zt, which is the error term of our previous regression. So zt is equal phi zt minus 1 plus another error term, where yt is a white noise. So the decay Fourier test is based on the fact of the hypothesis H0 that phi1 equal 1 versus the alternative hypothesis phi is module is less than 1, or H0 means zt is a random walk, while on the H0 zt is a stationary autoregressive. So using this assumption, we can compute a test statistic, and student statistic is not standard normal, and its limited distribution is called decay Fourier distribution, which doesn't have a closed form representation. So we just simulate critical value of decay Fourier statistic in order to make a decision on whether or not our variable is stationary. So to capture the non-zero mean, we can write this from with a constant in our models, in our previous model. So there are also a situation in which we can capture a non-zero mean or a linear trend by adding a trend term in our relationship. So we can use the same principle in order to test the stationarity of or the cointegration of our models. So we have also a augmented decay Fourier test. The augmented decay Fourier test assume that xt or ut is the white noise by adding enough lag in the differential of the error term of our regression relationship. On the right hand side, this properly could be guaranteed approximately. So we have to choose the choice of lag by using many criterion like Akaike information criterion or other criteria in order to help us take a decision about our test. So in this situation, we have to recapitulate what we have said since the beginning. So we have a var p between give a relationship between two variable and lag variable. So we have a reduced form, we have a structural form. In the situation in which xt and yt are stationary, we have a conventional stationary var, and in the situation in which we have both xt and xt integrated of order 1, and in the situation where there doesn't exist a beta, so that yt minus beta xt is stationary, we have a problem of spurious regression. So we can determine whether there is a spurious regression using augmented Tikefuller tests. So the situation in which we accept the null hypothesis in the Tikefuller test mean that there is problem of spurious regression. So what is really spurious regression? What is the manifestation of spurious regression? So we have Engle and Granger tests indicate there is not beta 0, so that yt minus beta xt is stationary. We have an example, monthly salary at Microsoft, and YT as a population in the developing countries series. Two series are totally uncorrelated. The two series are not, there is not possible relationship between monthly salary in Microsoft and the population in developing country, developing African city, for example. But the increase in xt and yt doesn't cause each other. So ordinary square of xt on yt will generate high R square because correlation, calculated correlation between the two variables is high, but ordinary least square is not reliable when spurious regression is present. So in the situation in which both xt and yt are integrated of order 1 and there exists a beta 0, so that xt minus beta yt is stationary. In the situation we reject the null hypothesis in Tikefuller test, it means that we should make a error correction model that we will present to you in a moment. So what is error correction model? So we have a representation of our model in which we estimate our variable in function of lack of orders. So we have a simple classical VAR here. So if we substitute we substitute the expression yt, which is equal to the differential of yt plus yt minus 1, and xt equal differential of of xt plus xt at the time t minus 1, we obtain the current relationship that the term in red in your screen appear in the two relationship, which can signify that we can estimate the differential of our two stationary variables in function of each other. That is error correction model. So in the case of structural VAR that is given here, you can also make a same substitution and have a similar term that appear in the two relationship between the differential of our variable. So which means that we can express the differential of our variable in a linear manner. So that is error correction model that we will present to you most widely in a moment. So how to fit error correction model? So Engle and Granger have two-step fitting this kind of model, error correction model. So we first fit ordinary least square of regression of yt in function of xt. So in this linear ordinary least square that we fit, since xt and yt are co-integrated, so that the alpha and beta 0 are co-integrated, we fit the relationship yt equal a certain constant theta multiplied by the differential of xt plus another coefficient multiplied by the error correction term, which is the residual of previous ordinary least square of our two variables. So this term, the term called the error correction term that we found in a previous relationship in red. That is the estimation of the differential of a variable in function of the differential of order, without forgetting the error correction terms. So that's the representation of error correction theorem. So to recapitulate ourselves, we can say that VAR model, in VAR model we have a reduced form and a structural form. In the case in which our two variables are stationary, we have a conventional stationary VAR. In the case in which we have our two variables integrated of order 1, in a situation in which our two variables are not co-integrated, we have a problem of spurious regression, and in the situation of cointegration, we need to estimate error correction model. And in the case we have only one cointegration relation, we have Engle and Granger test works. So what is there more than two? What if there is more than two variables? So we have x1, x2, and x3, for example. If we're confident that there wouldn't be more than one cointegration relation among terms, which means that cointegration is equal to 0 or 1. So Engle and Granger tests are fitted. We fit ordinary least square of third variable in function of each variable in function of order, and augmented decay Fourier test, and make augmented decay Fourier test on the residual. So if there is two cointegration relation in our variable, so there is a strong multicollinearity between the two first variables. So we have to estimate in the situation of which there exists a multiple cointegration relation between variable to make a vector error correction and Johansen test. So Johansen methodology has been made since 1988. So the drawback of Engle and Granger approach, what is it? It can only identify simple equilibrium relationship among the variables. If we have more than two variables in the model, then there is a probability that of having more than one cointegration relationship. So Johansen in 1988 proposed a framework of estimating and testing of vector error correction model based on vector autoregressive equation with which we can find out how many cointegration relations exist among variables. Johansen vector error correction model is more general for testing multiple cointegrating relationships when there are more than two variables. For k variable, we can have up to k minus 1 cointegration relationship. So in a k-dimensional vector error or vector autoregressive regression model with p-lags, we have a representation, the following representation of xt in function of lagged vector. So matrices P1, P2, Pk have a covariance matrix. So when xt is a vector of k times series at time t, and xt is a vector white noise with covariance epsilon. So if the variable from the VAR are co-integrated, the VAR model presented can be equivalently rewritten in the form of vector error correction as shown below, Engle and Granger in 1987. So we have a term in red which represents an error correction term, but in this case we have a coefficient, a matricial coefficient P that is being used in analog manner in the case of only two variables. So a k-dimensional vector error correction model for a VAR P process can be written as is given on your screen. So with the error correction term in red. So in the vector error correction, the differential of xt and its lag are all stationary. So pkk time multiplied by xt minus 1 is the error correction term, and the matrix pkk contain long-run relationship. So the rank of this matrix is a number of cointegration relationships. So if there are R or integration vector, the matrix can be expressed as the product of matrices of order Kr and matrix of order Rk. So alpha contains speed of adjustment parameter which interpreted as a way with which each cointegration vector appear in the given equation. Beta contain coefficient of long-run relationship. So we have many situations. If the rank of matrix P is 0, it means that xt is integrated of order 1 and not cointegrated. So the vector error correction is reduced to the differential of xt in function of the differential of lack of our variable. So the differential of xt follow a VAR p minus 1 models. You can remember that originally xt follow the VAR x p models. So if a rank of matrix is maximum, it means that P was full rank, so that xt is stationary. If it's coarse, we can simplify analysis. You can simply analyze xt directly. So if we have a rank of our matrix between 0 and k strictly, there are R cointegration relation, and P can be written as a product of two matrices where beta has R linearly dependent column representing the cointegrating errors, vectors. So you can notice that the products alpha beta is not unique, as you can see. But how to determine the number of cointegration relationship? The rank of the long-run impact matrix P equal to the number of cointegration, and it is evaluated to determine the number of eigenvalue that different from 0. And Johansen and Joselius in 1990 proposed two methods to determine the number of cointegrating relations. We have trace statistics based on likelihood ratio tests about the trace of the matrix. We have maximum eigenvalue statistics based on eigenvalue maximum obtained from estimation procedure. These cointegration tests are formulated in terms of estimated eigenvalue lambda e of the matrix P. So we have Johansen trace matrix, trace statistics. So the trace statistic consider whether the trace is increased by adding more eigenvalue beyond the earth eigenvalue. Consider the hypothesis. In our hypothesis, the rank is R0 or more than or superior to R0. The likelihood ratio test is given, and you can note that if rank is the rank of matrix is equal to R0, so all non-zero eigenvalues should all be close to 0, or a likelihood ratio statistic should be small that you cannot reject H0. So if rank of the matrix is superior to R0, then all non-zero eigenvalue should be non-zero but less than 1, and the likelihood ratio statistic should be larger should be larger. So Johansen maximum eigen statistic, it is sequential procedure to determine the number of cointegration. Consider the hypothesis H0 rank of P equal R0, or the alternative the rank of P is equal to R0 plus 1. The test statistic is given by negative T on multiplying the logarithm of 1 minus the likelihood of order R0 plus 1. So we can note that the test consists of ordering the largest eigenvalue in descending order and considering whether they are significantly different from 0. Suppose we obtain a n eigenvalue noted lambda 1 to lambda k. If the variable under are not cointegrated, the rank of P is 0 and all the eigenvalues should be equal to 0. Therefore, the logarithm of 1 minus lambda e lambda I equal to 0. So the asymptotic null distribution of both tests are not chi-square, but instead of complicated function of Brownian motion, and the critical value of the statistics are non-standard. Critical value of both statistics are provided by Johansen and Joselius of since 1990. So maximum likelihood estimation of cointegrated vector is the method required in order to estimate a parameter. Once we found the rank of matrix P, then the cointegrated vector can be written. So we have the cointegration, the cointegrated relationship, the relationship between differentiated variables that are given in the relationship that you see on the screen. And in this relationship, we have the error term, which is Gaussian white noise. So reduced rank multivariate regression. Johansen derived the maximum likelihood estimate of parameter under the reduced rank restriction. So the estimate of beta coefficient are given in by the eigenvector associated with the eigenvalue, each eigenvalue. So we first estimate beta 0 using MLE block and in beta 0, and the MLE of the remaining parameter can be estimated by ordinary least square, since the variables are cointegrated stationary. So we have the relationship that is given below. So we can know that Johansen approach estimate beta using MLE instead of ordinary least square, which use an Engle and Granger two-step as if R is superior to 1 may cause multilinearity. So maximum likelihood estimation, we consider two multivariate regression. The first is the differentiated regression, the relationship between differentiated vector and lags till order p minus 1, and we have the estimate of lag vector in function of differentiated lag vector. So in this situation, we we solve the relationship to denote the eigenvalue and eigenvector pair by that is given there. So we have to recapitulate. To recapitulate, we can say that we have the P model, we have the reduced form, we have a structural form, we have a situation in which both xt and yt are stationary. We have a conventional stationary VAR in this situation. But in the situation in which we have both xt and yt co-integrated, and there doesn't exist a relation a beta zero, so that xt minus beta yt by so that yt minus beta xt is stationary, have problem of spurious progression. But in the situation in which there exists a beta, so that yt minus beta xt is stationary, we have error correction models. So only on cointegration relation, in the situation we have only one cointegration relation, we estimate a Engle and Granger test. In the situation in which we have many cointegration relation, we have vector error correction model and Johansen test to run. So key time series regression trend we have without integrated of order one. Everything discussed before can be described by VAR1. So, and VAR1 can be solved considered consistently and efficiently by least square, and thus have no difference with ordinary regression with possible serial correlation. Deterministic trend and stochastic trend will cause spurious result in regression due to integration of order one residual. So trend can be eliminated through differentiating, but cointegration analysis provide a better alternative when applicable. Stationary series can be modeled with linear regression directly. Series with stochastic trend can be modeled by order Q differential. So what we have done so far was to present to you theoretical foundation of VAR model. And now you know how to estimate which method you to use in order to estimate VAR model. And we now showing you after an estimate of GDP growth rates in function of term spread. And as following the discussion on the non-stationarity of GDP growth, we use data from Q1 of 1981 to Q4 of 2012. So the two model equations are given on your screen, in which we express the GDP at current time in function of lag 1 and 2 of GDP and term spread, as well as term spread of current term, which is expressed in linear combination of GDP and term spread of period of lag 1 and 2, as without forgetting error term in every K. So it's used as is done in VAR vector autoregressive model. So you see the specification which comply with theory that we just shown to you a little bit sooner in this video tutorial. So after estimate using maximum likelihood method, we have the estimate of every equation. In the left hand side of your screen, you have the estimate of GDP at time t, which is expressed at in function of our different lag variable of period 1 and 2, lag 1 and 2 lag variable. So we have in the first in the first column, the second column, the coefficient, the estimate coefficient. We have in the last column the p-value, which measure the significance of every coefficient. We have the coefficient of growth of lag 1, which is 0.28, and the level of significativity is 10%, as is the same for GDP growth lag 2, as well as term spread of lag 1. The lag 2 term spread is the only variable that is significant at 1% rate, and you can interpret the coefficient of term spread of lag 2 term spread as an elasticity, which means that when the the lag 2 term spread increased by 1%, the GDP growth of current period increased by 1.32%. Which means that making an action in term spread will wait for 2 periods of time, which means a half of year, in order to see a reaction of GDP growth. If you take a level of significativity of 1% or 5% as well. In the second, in the right hand side of your screen, you have an estimate of term spread of current period in function of lag of different two variables, which are growth rate and term spread. So the only variable significant at 5 and 1% level is term spread, is lag term spread, and the coefficient is 0.5, which means that when the term spread, the lag term spread increase by 1%, the term spread of the following period increase by the almost 1%, almost the same rate. So you don't need to wait for 2 periods in the previous case, but 1 period is sufficient to have an action of variation of term spread of lag term spread in term spread, which is the dependent variable in this case. So after this estimate, we can substitute our coefficient in our equation to obtain the linear representation of GDP and term spread in function of different lag variable, and you see different constant, different coefficient that are put into the equation, and the function VAR, the VAR function can be used to obtain the same coefficient estimate as presented above, since it applies ordinary least square per equation 2. So this equation can be used in order to make prevision as well as simulation. So we can make simulation. Elasticity, as I told you, can be used in order to see what is the effect of dependent variable while our independent variable fluctuates. So VAR model can be used to measure the impact of a variable of another, and the size of the impacts as well as prevision that we are going to just present to you right now. And a prevision is used in a direct multi-period forecast that forecasts each period into a future using a model of YT and an additional predictor XT with P lags. In some, it's done first estimating our variable YT in function of previous preview observe variable in this manner that you can see on your screen, which is then used to compute the forecast of y at the period t plus h based on observation through period t. And so the direct multiple period forecast, for example, to obtain 2 quarter ahead forecast of GDP growth and the term spread, we first estimate the equation GDP in function of other lags variable as well as term spread, and then substitute the value of GDP growth of term growth of 4 quarter of year 2012 as well as GDP of quarter 3 at the same year, the same situation with term spread and both in both equation. And when after this substitution, this is very easy done manually, but generally software have section that allows you to make prevision based on data. So that's it for this tutorial. We hope it helped you very well understand VAR models, and in the next tutorial we will show you how to practically implement VAR model in eViews. So thank you very much for listening to us. Bye bye.